right, let's talk about wave properties. And we can't talk about wave properties without talking about periodic motion. And if you've taken pre-calc or if you're in pre-calc, that's hopefully something that you've talked about. What we're going to consider is a pendulum. Now, this PowerPoint is supposed to have GIFs in it, like this is supposed to swing back and forth, but it's not working from this computer. So we're just going to pretend that this pendulum is swinging back and forth, just as a visual. So the resting position of a pendulum or spring is called equilibrium. So that would be when this pendulum is at the very bottom, when it's just hanging there, when it's completely at rest. That's the equilibrium position for this particular example. If I want the pendulum to move, I have to apply a force. There has to be some introduction of more energy than the pendulum already has in order to get it to do something other than what it's doing. Now, over time, because this is real life and there is a loss of energy, it is not a closed system, the pendulum will eventually slow down, and this is called damping. If we could have an ideal pendulum, meaning we can exclude or ignore or take out outside forces and we can make a closed system, then the pendulum would swing back and forth forever because there would never be anything that's taking or introducing energy to or from the system. Now, this back and forth repetitive behavior is called simple harmonic motion, which makes sense. It's simple, it does one thing, it goes back and forth. It's harmonic because it's repetitive, and the motion is self-explanatory. All right, so what I want to do is take, and again, this is supposed to be bouncing up and down. This is something on a spring. It has this resting equilibrium position. If we can imagine this being pulled down and then let go of. And what would it do? It would bob up and down in this very simple harmonic nature with an equilibrium position where it would be at rest. So I'd like to graph this over time on my graph here. So let me grab, I like green. All right, so I'm going to label some things here. I'm going to let 2 squares up be 1 and 2 squares down be -1. And this is going to be position here. So let me see if I can write sideways. Oh gosh. Okay, you can make fun of me, but only because I said so. Position, and what's it going to be measured in? Well, it doesn't really matter here, so I'm going to pick meters because that's my standard unit for physics. Okay, so that's position on the y-axis, and on the x-axis would be time. So this is going to be time. Could went a little bit better. In seconds, standard unit for time. Okay, and I'm going to let every 2 boxes be 1 second. So that's 1, 2, 3, 4, 5, 6, and 7 seconds. Now let me switch colors. I'm a fan of orange. Okay, so if the mass here on a spring started off at an equilibrium position, we would call that position 0. And then let's say this springs up first. So what's it going to do? Over time, its position is going to increase, or if we consider up to be the positive direction, it will get farther away from its equilibrium. And the pace at which, the rate at which it does that will slow down as it reaches the peak of its trajectory. Think about a projectile. So this is going to go up until it reaches some height, and then it's going to come back down. And even though I'm terrible at drawing on the computer, that kind of looks like half of a sine curve. What does it do after it comes back to its equilibrium? It goes down, and then it comes back up in the same kind of way, but just dipping in the negative direction. And then it repeats itself. And assuming no loss of energy, which we are, oh, this is terrible, we would get a lovely sine curve that would, in theory, continue on into infinity unless there was some introduction or extraction of energy from this system. A few terms that we'll need to know. First one is the period of a wave. And that's just how long it takes the wave to go there and back. If it's a pendulum, to go all the way up to one side, back to equilibrium, all the way up to the other side, and then back to where it started. If it's a spring on a mass, like the previous slide, it's the time it takes for it to go up and then down and back to equilibrium. You get the point. A sine curve, one full cycle of a sine curve or a cosine wave. Another term that we've got to know is frequency. And this one is one we're very familiar with, I hope. And it's just the rate. It's how many vibrations or cycles per unit of time. So it's generally like how many waves per second, how many swings to and fro per second. And it's measured in hertz. So one cycle per second, one wave per second is 1 hertz. And there's a really simple way to go from one to the other. And this makes sense when you think about the units. The period is just measured in seconds. Frequency is measured in something per second. It's cycles per second or a number per second. So they're really just inverses of each other. So here's our nice simple formula. And I've already solved it for you so that you have it for period in terms of frequency and you have it for frequency in terms of the period. A couple of other terms we've got to know. The wavelength is from any one point on a wave to the next occurrence of that same point on the wave. So if it's from a peak to a peak, we call these crests, or from a trough to a trough, that's the very bottom, or from, as you see here, from some random point on the wave to that same random point on the wave. That's the wavelength. And it will be the same measured anywhere on that wave as long as the wave itself doesn't change. Amplitude is just from the equilibrium up or down to a maximum height or a maximum low point, a crest or a trough. All right, and I'd like you to take a second, pause the video, read these questions and try them yourself, and I'm gonna go over them. Okay. So a pendulum is observed to complete 23 full cycles in 58 seconds. So here's the number of cycles, here's the amount of time, determine the period and the frequency. Okay, so the period is 1 over the frequency, but like they didn't give me the frequency or the period, so how am I going to use these formulas? Well, if I think about the previous slide and what period and frequency actually are, I can figure it out. What is the period of a wave? It's how long it takes the wave to complete a full cycle. So it's seconds per cycle. So if we do 58 over 23, that will get us, that's seconds, and this is cycles. So if we reduce that, if we actually do 58 over 23, we will get the period, which is like 2.52. I'm gonna squiggle 2.52 seconds per cycle. Or you can just put seconds, I'm fine with that. Okay. And then the frequency is just 1 over that. So the frequency is, well, or we could just switch these numbers, but same difference. You can do 1 over this 2.52 number, or you can do 23 over 58. And that would be cycles per second, which is a hertz. So for the frequency, we are getting 0.4 hertz. H, capital H, Z. All right. So for number 2, a mass is tied to a spring and begins vibrating periodically. The distance between its highest and lowest position is 38 centimeters. What is the amplitude of the vibrations? So that's a lot that they just said. I'm going to draw a picture to try to figure out what they're actually asking for. It says the distance between its highest and lowest positions is 38 centimeters. So that means if I draw a wave, the mass on the spring goes up, it goes to equilibrium, it comes back down, and then it comes back to equilibrium. if the distance between its highest and lowest points is 38 centimeters, if this whole distance is 38 centimeters, then the amplitude is half of that, because the amplitude is just from the equilibrium up or down. So the amplitude is half of 38, which is 19. There we go. So we can't talk about waves without talking about mediums. Here's a random example in real life: newspapers, the news media. So sometimes the information is carried to you through a physical newspaper. Most of the time now, it's carried to you through the internet. But the medium is how that information is relayed to you, the platform through which the information gets to you. So a medium is just a substance or a material that carries the wave or the energy. So in our life, it would be like water or air, or maybe glass, or something other than water or air, some different kind of gas or something. The medium is not the wave itself. It's just the means of transfer. It's like the vessel that carries the energy from one point to another. Another example that I think about is with art. So you have an idea in your head and you have to pick a medium that best translates that idea. So sometimes you use a canvas and paint. That would be the medium. And whatever the product is, that would have been the idea or the information or the energy. If you choose to use clay or some sculpting material, that's different, and you're translating your idea using a different medium. So the wave itself is a disturbance of the medium. The medium would be there whether there's a wave or not. What happens is there's a disturbance to that medium, which that medium then carries because the particles in the medium are interacting. So the wave is transporting energy through the medium itself. There's no matter actually transferred. When you make a little wave in a rope like this picture is showing, the rope itself is not moving from point A to point B. There is a disturbance which travels through the length of the rope and then probably comes back, but the rope itself is only moving up and down. It's not actually moving left or right. So how much energy a wave can transfer is affected by the amplitude of the wave, the frequency of the wave, the wavelength of the wave. More amplitude is higher energy. I think that's pretty intuitive. And if you have a lower amplitude, that's a lower energy. Higher frequency is higher energy. And take a moment and try to answer this question. Pause the video. Give it a go. So a medium is able to transport a wave from one location to another because the particles in the medium are blank. So are the particles in a medium frictionless? Probably not. So I think we can eliminate A. Are they isolated from one another? Probably not. Maybe they're individual, but they're interacting. They may be even spread out, but they're still interacting. So I think that gave us our answer. We should have picked C. They're able to interact. All right, so more on waves in the next lecture.